Hey everyone, Techie here. Welcome to today's explainer. Okay, if you've spent, literally any time looking at API documentation, you have definitely seen these terms popping up absolutely everywhere. Get, post, and delete. Now, you might think they're just arbitrary technical jargon, right? Like just some random words chosen by programmers years ago. But I am here to tell you, they are not random at all. They actually represent the fundamental rules of the web. Specifically, they're the rules of REST architecture. So today, we are going to demystify what these terms actually mean and how they structure the way information flows to make the modern web infinitely scalable.
Welcome to AI Tech Hub. For today's explainer, we're breaking things down into two simple parts. Section 1 explores the core rules, and Section 2 puts those rules into practice.
All right, let's dive right into this. Section 1, the rules.
So REST is basically a very strict architectural blueprint, and the absolute first rule of this blueprint is identity. Every single resource gets its very own highly specific URL. A resource is honestly just any piece of data that you care about. Take the URL tods/5. That is a unique address. It doesn't just point to some general to-do list somewhere, it points exactly to item number 5. You see, to interact with a piece of information, you first need its exact address, and then you need an action verb to tell the server what you actually want to do with it. Let's quickly fire off our very first HTTP method, GET. As the core rule dictates, GET simply reads the resource. When you send a GET request, you're basically telling the API, hey, go look up the data at this specific address and send me a copy back. Crucially, and this is a big deal, GET is strictly what we call a safe method. You are not altering the data, you aren't deleting anything, you are literally just reading it without causing any side effects at all.
But obviously, we don't just want to read data all day, right? We need to add to it. So we immediately follow up with the post method. Post creates something totally new. When you use post, you're sending a fresh package of data to the server, and the API takes that payload and uses it to construct an entirely new resource from scratch. It is exactly how you dynamically build and expand your whole data structure.
Now, what if you need to fix a typo or change some existing information? That's where a put comes in. Put updates it. You send the new data to that exact same URL and it completely overwrites the old data. There's a brilliant technical concept here called idempotency. I know, fancy word, but it just means put is idempotent. You could send that exact same put request 100 times in a row and the end state of that resource remains exactly the same. It just replaces the whole thing over and over again.
And to finish off our rapid-fire look at these methods, we have delete. As you can probably guess, this one straightforwardly removes the resource. Send the delete request to our example /todos/5, and the server just wipes that specific item right out of existence. Simple as that. It is also idempotent, by the way. So we've got get to read, post to create, put to update, and delete to remove. Those are your action verbs. But there is one more overriding rule that governs this whole shebang.
Let's slow down for a second, because this is an absolutely vital concept, the stateless server. In a true REST architecture, the server literally has the memory of a goldfish. It never, ever remembers your last request. Every single call you make has to stand completely alone. If you make a GET request and then you follow it up with a delete request a second later, the server has no idea who you are from that first GET. You have to pass all your context, like your authentication tokens and credentials, every single time you ask for something. And this goldfish memory? It's actually a superpower. It's exactly what allows REST APIs to scale so massively, because any server in a massive global cluster can handle any request at any time without needing a history lesson on what you were just doing.
Let's move on and see how this all builds together. Section 2, in practice. All right, let's walk through a real API interaction to see how these pieces, the methods, the statelessness, and another incredibly critical component called status codes, all actually work together. Say you hit the general/todos endpoint with a GET request. You're asking the server to read the entire collection. The server processes this independent, completely stateless request, gathers up your complete list, and sends it back. But it also pairs it with a status code, specifically a 200 OK. This is the server's way of letting you know, yep, the read operation succeeded perfectly. Now let's flip it. What if you send a post request to that exact same /todos endpoint, but this time you attach a JSON body containing the details of a brand new task? The result shifts entirely. The server reads that JSON payload, understands you want to build something new because you used the post method, creates the new item, and fires back a 201 created status code. It's the exact same URL endpoint, but an entirely different action and a totally different server response. It's like magic, but it's just really good architecture. And boom, that's REST. Not just in theory, but actually running. It's clearly not just a bunch of random jargon, right? By combining a unique URL, a highly specific method like GET or POST, pairing it with clear, standardized status codes, and operating under that strict rule that the server processes everything statelessly, we've achieved highly structured, perfectly scalable data in motion.
I really hope this explainer made the whole REST architectural blueprint crystal clear for you. If you want to dive even deeper, drop the keyword REST in the comments and I'll send you a real project build using everything we discussed today. But before we go, I want to leave you with a bit of a brain teaser. If REST is completely stateless and servers truly have the memory of a goldfish, how on earth do streaming platforms maintain continuous, real-time data feeds without breaking the rules? Definitely something to think about. Keep learning and I'll see you in the next one.